Today's goal of this lecture. Today I will see some example based on reducibility and irreducibility. Because I have told you more times, this concept actually very important for higher study. At first I will hardly recommend you, if you don't see my previous video, at first see my previous video. Then today's goal of this lecture would be so easy. This is our first goal of this lecture. At first I will see some example. Then I will see theorem based on this reducibility and irreducibility. Okay. My first example which had come in session net exam. Option 1. Fx equal to x square minus 5. Here the question, which of the following polynomial is irreducible in Z? We all of us know if the polynomial is primitive polynomial, then irreducibility in Q always imply irreducibility in integer. Notice here GCD of 1 and 5 is 1, so obviously the polynomial is primitive. Notice here x square minus 5 means x plus square root of 5, x minus square root of 5. Since square root of 5 does not belongs to the rational number, so cannot reduce this polynomial in rational number. That means in rational number this is irreducible, and since the polynomial is primitive polynomial, then irreducibility of rational number always imply irreducibility in integer. So this polynomial is irreducible in integer. So at first I will see third option. 1 plus x square plus x cube plus x to the power 4. In my previous video I have seen this is the cyclotomic polynomial, and when p equal to prime number in here p equal to 5, then always this is irreducible. So I have told you why my previous video is very important. If you don't see my previous video, then you cannot understand what is actually the cyclotomic polynomial. For p equal to prime number 5, this polynomial is irreducible. Here, this is cyclotomic polynomial for p equal to 5 and 5 be a prime number. So, obviously, this is irreducible in Q, and since this polynomial is primitive polynomial, so irreducibility in Q always imply irreducibility in Z. So option 3 is right option. Option 2 also right option, because here I have got this type of polynomial is irreducible in Q, and by the property of Eisenstein criteria, f of x plus alpha is irreducible. That imply f of x is irreducible. Here this polynomial just replace x plus 1. So by the property of Eisenstein criteria, since this polynomial is irreducible, so obviously this polynomial is irreducible. I hope my all viewers have understood. And option 4, 1 plus x square plus x cube. We can write this as 1 plus x times x square times 1 plus x, and this imply 1 plus x times x square plus 1. Therefore, we can reduce this polynomial 1 plus x square plus x cube as 1 plus x times x square plus 1. So, this polynomial is reducible polynomial. And since this is reducible in Q, obviously this is reducible in Z because this polynomial is primitive polynomial. Okay. My next question, here fx equal to x square plus 3x minus 1, and this polynomial always irreducible over Q because here I will apply mod p test. If we consider the prime p equal to 2, then f bar x would be x square plus x minus 1. In Z2, notice degree of fx and degree of f bar x is always same. So obviously we can apply the mod p test. Also p be a prime number. Then f bar 0 is not equal to 0 and f bar 1 also not equal to 0. Since the degree of the polynomial is 2, therefore we can obviously apply the root test. So obviously this polynomial is irreducible over Q. Since the polynomial is irreducible over Q, so by mod p test we can tell our given polynomial fx is irreducible over Q. So option 2 is a right option. And option 1 and option 3, notice option 1 given f is irreducible over z square root of 13 and option 3 given f is irreducible over q square root of 13 for this. Next, fx equal to x square plus 3x minus 1. If fx equal to 0, then that implies x equal to minus 3 plus minus square root of 9 minus 4 times 1 minus 1 over 2. That means this implies minus 3 over 2 plus minus half square root of root 13. Notice, we all of us know q square root of 13 means obviously the element look like a plus b square root of 13 where ab belongs to q. This type of element, x be the member of this type of element. So the element are look like obviously a plus b square root of 13 type. That means since here the root is this type, so we can write the root such type x plus 3 over 2 plus half square root of 13 times x plus 3 over 2 minus square root of 13 over 2. The root would be such type, and this is belongs to q square root of 13. So obviously third option is a right option. F is reducible q square root of 13. Option 1 is also right option. Here notice, here given f is irreducible over z square root of 13. Z square root of 13 means we all of us know this is a plus b square root of 13 where ab belongs to integer. Here the root of this polynomial is such type. Notice this is belongs to q, not integer. So this root belongs to q square root of 13. But this root does not belongs to z square root of 13. Therefore, we cannot reduce the root in the field z square root of 13. So f is irreducible in z square root of 13. I hope my all viewers have understood this is okay. Now I will see some maximal and prime ideal in ZX. I will see some theorem actually based on maximal and prime ideal in ZX. Let Px be the member of ZX be irreducible polynomial. Then the ideal generated by Px is prime ideal but not be maximal ideal. That means if the polynomial in ZX which be irreducible polynomial, then the polynomial which is generated by this irreducible polynomial, this is prime ideal but not be maximal ideal. Why? Notice in ZX consider the polynomial 1 plus x square. Obviously we all of us know in ZX the polynomial 1 plus x square is irreducible. Then the ideal generated by 1 plus x square in ZX, this is, since this is irreducible, this is prime ideal but not be maximal ideal. Okay. My next theorem is, and every maximal ideal in ZX is of the form ideal generated by P, Fx, where this Fx is irreducible polynomial over ZX. Qx, actually every non-zero ideal is a maximal ideal if it is prime ideal. That means in Qx, the ideal generated by polynomial which is irreducible, then this is maximal and prime both. But in ZX this is different. If this is irreducible, then this is prime ideal but not be maximal ideal. In ZX the maximal ideal is look like ideal generated by P, Fx, where P be a prime number and Fx is irreducible polynomial in ZX. For example, consider ZX modulo ideal generated by x square plus x plus 1, 2. Obviously, by previous rules, this would be isomorphic to Z2x ideal generated by x square plus x plus 1. And notice, we all of us know x square plus x plus 1, it has no root when p equal to 2. So, this is irreducible polynomial. Since this is irreducible polynomial, so we can tell this ideal generated by x square plus x plus 1, 2 is the maximal ideal, which is, and this ring is isomorphic to Z2x ideal generated by x square plus x plus 1. Now I will see why we can write this quotient ring as this type. This corollary we can tell let f be a field and px is an irreducible polynomial over the field f. Then fx modulo ideal generated by px is always be a field where this px is irreducible polynomial and f be a field. As for example, we all of us know Z2x be a field and x cube plus x plus 1 is irreducible polynomial in Z2x. Since this is irreducible polynomial, so Z2x modulo ideal generated by x cube plus x plus 1, obviously this is isomorphic to, always be field, this is isomorphic to field, and this field is look like here the polynomial ax square plus bx plus c plus ideal generated by x cube plus x plus 1, where this a belongs to Z2, this b also belongs to Z2, this c belongs to Z2. So, here can be 2 element, here also can be 2 element, here also can be 2 element. So 2 cross 2 cross 2, that means here, since this is the irreducible polynomial in Z2, so obviously this is field, and this field is isomorphic to F2 to the power q type. This field contain actually 8 element. The ideal generated by x square plus x plus 2 in Z5x, obviously this polynomial is irreducible. Just check it by root test we can tell. So obviously Z5x ideal generated by x square plus x plus 2, this is isomorphic to a field. And how look like the field? This is Z5x ideal generated by x square plus x plus 2. This element is look like fx plus ideal generated by x square plus x plus 2, where this fx belongs to Z5x. That means similar to before, this would be such type ax plus b plus ideal generated by x square plus x plus 2, where AB belongs to Z5. That means this is actually isomorphic to, since here A belongs to Z5, B also B belongs to Z5, therefore this is actually isomorphic to F5 whole square. Here we can tell ZPX over Fx is always isomorphic to the field f to the power p to the power r, where obviously what is the r? R is the degree of the polynomial fx. R is the degree of the polynomial which is given this is isomorphic to the field, because obviously this polynomial be irreducible, and this polynomial isomorphic to f to the power pr, where r is the degree of the polynomial fx. Okay, see, in Rx the ideal generated by x to the power 4 plus 4 is this ideal is maximal ideal. Notice, is this isomorphic to field? This is my question. We all of us know in Rx, when the polynomial degree of the polynomial is greater than 2, then be reducible. Degree of polynomial of greater than 2, this type of polynomial always be reducible in Rx. We all of us know this is, since this is reducible polynomial, so this cannot be isomorphic to field, and since this is with the field and this is not be reducible, so this cannot be maximal ideal. I hope my all viewers have understood the actual idea. Okay, well, I'll stop here. In my next video I will discuss this part again, because this type of question, when any quotient ring is isomorphic to field, when the polynomial be maximal, when the polynomial be prime ideal, this type of question actually very important for not only competitive exam, this is important for higher study also. So in my next video I will discuss this type of question again. Okay, see you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.